Hi everyone, welcome back to this chemistry series video in which today I'm going to be talking about solubility and specifically the rules in relation to solubility of how certain compounds are able to dissolve while others cannot. So without further ado, what is solubility? Well, solubility is defined as the ability of a solute to completely dissociate within a solvent. So for example, in this video shown here, we have an Alka-Seltzer that is completely dissociating when it is dropped within water and it's causing the solution to turn yellow. I often take Alka-Seltzers when I feel like I have a sore throat, and that is a perfect way to dissolve the compound so that way you can ingest it in order to hopefully feel better. But it comes as a tab, and then afterwards, when you drop it in water, the whole tab is going to completely disintegrate and be integrated within the water. Now, the opposite of solubility is known as insolubility, which we can also call precipitation. You might have heard of precipitation before, like in the weather report where they say, oh, there's going to be a lot of precipitation today. Precipitation means that you have a lot of rain in a certain area, at least when we're talking according to meteorology terms. However, in chemistry terms, we define precipitation as the ability of a chemical compound to come out of solution due to the fact that it is insoluble. So in this flask right here, I've incorporated a solid that has come out of solution, and many times a precipitate, it'll be found at the bottom of a chemical flask because solids are, for the most part, with the exception of ice, denser than their liquid form, so to say. So many times you will find them at the bottom of a flask, oftentimes at a certain corner of the flask if you tilt it in a certain way. So precipitation reactions are pretty useful because they can generate certain solids by mixing together certain ions that are dissolved within the liquid. And this is where I get into my solubility rules. I know on Google there's quite a bit of solubility rules out there, but there's been mnemonics that have been shortened. I want to give credit to the original YouTube video that I found that came up with this mnemonic, and I'm simply re-reporting it. I'll link the video that originally listed the mnemonic down below, so you could go check her out. I just chose to incorporate it, as well as a couple rules, because while that video did a fantastic job explaining the first slide of the mnemonic I'm going to show, I also made a second one to incorporate more rules that this first mnemonic didn't cover. So the mnemonic goes as such: nag, sag. Think about it this way. Nag, sag is kind of an easy acronym to remember. To nag someone is to like pester them, and then sag, think of sagging your pants. That's the way I think of nag, sag. Whatever helps you remember it, that's what you got to do, essentially. So something that's always soluble, they're going to be nitrates, acetates, group 1 elements, such as potassium, sodium, all those different group 1 elements, sulfates as well, and then ammonium, as well as group 17, which are all halogens. All of those guys are going to be soluble within each other. And there are some exceptions, which I want to highlight, which I like using the acronym PMS. P, it stands for PB, which is lead. So lead is quite insoluble. Mercury is also insoluble, which is the M, but the chemical formula is Hg. And then silver is the S in the PMS. However, its chemical formula is Ag. So PMS, quite an easy one to remember, as well as Castro-Bear. Ca in Castro is calcium. Str, strontium, is Sr. And then Bear is barium. So those 3 elements are also going to be generally insoluble. Those are the exceptions when it comes to that table. However, I do want to point out that there are more rules which the other mnemonic didn't quite cover, and there's really no other way about it except just to straight up memorize it. Luckily, it's not that hard because we're covering carbonates and phosphates. In biochemistry, you see carbonates and phosphates a lot, which is why it's very important to note right here. So the only things that can dissolve a carbonate and a phosphate group are only group 1 as well as ammonium groups. Other than that, it's going to be insoluble in everything else. So for example, it's not going to be soluble in any of the other compounds that we have listed under NAG-SAG. Big reason why is because the other compounds in NAG-SAG are anions. So it's only going to be soluble with the cationic compounds in NAG-SAG, given that carbonate and phosphate themselves are anions. I also want to point out that hydroxides and sulfates, they are actually going to be soluble in group 1 as well as ammoniums as well, but they're going to break the exception rule of Castro-Bear in that Normally, castor bear would be insoluble with everything it touches. However, in the case of hydroxides and sulfates, castor bear is going to be pretty soluble. So that's why I wanted to point out those two exceptions. Because NAG-SAG, it doesn't encapsulate everything, which is why I had to make this extra table for carbonates and phosphates as well as hydroxides and sulfates. You will see hydroxides a lot when it comes to acids and bases. Anyway, I wanted to go on to this question in which if a chemical flask has sodium sulfate as well as potassium fluorate, will a precipitate form? Will those two compounds end up forming a precipitate? And in order to answer that question, we need to go back to the solubility rules because we know that potassium sulfate, potassium falls into group 1 element, and then sulfate is a sulfate, which is part of NAG-SAG, and fluorate, potassium fluorate, is also going to fall under group 17, given that fluorine is a halogen. So sodium is a group 1 element, potassium is a group 1 element, sulfates fall in NAG-SAG, and then halogens also fall in NAG-SAG. So all of these ions are going to be completely soluble with each other. So as a result, we are not going to form a precipitate because all of the ions are soluble. Now for our next question here, a little trickier. Will a solution that has ammonium carbonate and lead nitrate form a precipitate? Well, we need to look now in the second table that I provided after the solubility mnemonic because we're dealing with the carbonate group. So ammonium carbonate is going to be soluble because we've already established that carbonates dissolve only with group 1 as well as ammonium ions. So it's going to be soluble for that reason. And when it comes to lead nitrate, however, we do have nitrates in the N of the NAG-SAG. However, lead is in the exception group. So lead, when it's combined with nitrate, is going to be insoluble. So our insoluble compound that we're going to produce is lead nitrate. So will it form a precipitate? Yes, it will. And the precipitate will be lead nitrate. I hope that this video helped clear up any confusion you might have had around the solubility rules, because I know that there's a lot of different charts out there and it can be confusing to process them all. And it seems like they all say different things. I want to thank you guys so much for watching this video. And this series is not done yet, at least the part with solubility, because if you look at that arrow, there's a video. I'm going to continue this series with a part 2 dealing with KSP calculations. I look forward to seeing you then.